Bismillahirrahmanirrahim. Now we'll start chapter 5. It's mainly about higher order linear differential equations. What I did concerning the book, I combined all the three sections, 5.1, 5.2, 5.3, on the same as one section. Let me say as one section. What we have in these three sections mainly in 5.1. We are talking about second order differential equation. He talk about the theoretical part, and how to solve it. Then he went to the general, to the nth order, to the higher order, nth order, second, third, fourth, blah, blah, blah. In 5.2, he talked about theoretical part. And then in 5.3, he talked about how to solve it. Actually, mainly we are talking about solving differential equations, linear differential equations with constant coefficients. More than constant coefficient, it will not be easy, and we will deal with part of it in chapter 11 when we talk about the series solution. Okay. So we have theoretical part and how to solve it. So I will start with the theoretical part. I'll combine the nth order differential equations in 5.2 and 5.1. It's the same idea. So no need to make it in two different places. When we talk about the nth order, what we talk about the nth order, it will be applied to the second order easily. So this is the way I will do it. Because of that, I started with the nth order. In 5.1, he talked about the second order only. That's it. He make it only differential of second order differential equation, second order differential equation. Okay. So now let me define the main terminologies. We say it's linear if it is in this form. An nth order differential equation is linear. It is in this form. I have function of x times the nth derivative of y, function of x times the nth minus 1 derivative, and so on. So notice they don't have any product of y or y prime or y double prime or any of these derivative times y square, nothing like that. And these functions should be continuous, and also the right hand side. Okay. And b0 of x not equal to 0, because if it's equal to 0, then it will not be nth order. It will be the nth minus 1 order differential equation. And also we say the equation is homogeneous. As I said, just in this slide or in the next few slides, we're talking about the terminologies to be sure that we understand the terminologies we have. So we have linear, we talk about it. Homogeneous, it depends on the right-hand side. If the right-hand side is equal to 0, we say it's homogeneous, which is f is 0, identically 0. Otherwise, we call it non-homogeneous. And by the way, how to solve non-homogeneous, we'll talk about it in section 5.5, where we have two methods, and determine coefficients and variation parameters. If we want to have this coefficient of the highest derivative, if we want to have that coefficient to be 1, we just divide by that to get this equation, which they call it standard form. This will be standard form. And usually to deal with the non-homogeneous, we need to deal with the associated homogeneous equation. Okay. Now we have what's called principle of superposition, which is an easy thing. Well, it means what? If we have solutions, y1, y2, up to yn, are n solutions, or if you have solutions, a linear combination is also a solution. The linear combination is also a solution. Now, that will help us towards what? That means if I have the set of all solutions of the homogeneous linear second order or nth order, same idea, it will be a subspace. That set will be a subspace. Because if I take two solutions, their sum as a linear combination, because I can take C11 and C21, assume I have two solutions, Y1 and Y2. The sum, for sure, C1Y1 plus C2Y2 is also a solution. If I take C11, C21, means their sum is also a solution. And any product of any constant, which is very clear from this one, is also a solution. If you remember how to say a set subspace, if we satisfy these two conditions, the sum is contained in the set, and also the multiplication by scalar is also in the set. So because of that, we call it subspace. So we call it the solution space of the differential equation. Okay. By the way, how to verify a function is a solution? Just you substitute into the equation. If satisfy the right-hand side equal to left-hand side, then it's a solution. And for example, if I want to show this one, cosine x is the solution of this equation, what I will do, I just substitute. I do y1 prime. That will be minus sine x. Y1 double prime. That will be minus cosine x. So to check, I put it in the equation. Why I'm doing y up to y double prime? Because the equation has y double prime. So I need to check left-hand side, which is y1 double prime plus y1. That will be what? Minus cosine x plus cosine x, and that is 0, which is the right-hand side. So that means right away y1 is a solution. Okay. I'll do the same for y2. Y2 will be sine x. So y2 prime will be at x, yeah, as a function of x. It will be cosine x. Y2 double prime will be minus sine x. I'll do the same, left-hand side. Y2 double prime plus y2. That will be what? Minus sine x plus sine x. That's equal to 0, which is the right-hand side. So y2 is also a solution. Now, this theorem, theorem 1, will give us what? Implies into any linear combination, C1 y1 plus C2 y2, which is C1 cosine x plus C2 sine x, is also a solution. And for example, he said y equal 3 cosine x minus 2 sine x is also a solution. This is solution. Any linear combination will be also a solution. Actually, this linear combination, we'll call it the general solution later, if they are linearly independent. In this case, sine and cosine are linearly independent. Okay. So that's mainly the idea in this theorem. If we said verify, these are solutions. How to verify these are solutions? We do just a calculation. And I need now the third derivative. So I need y1 of x equal e minus 3x. Y1 prime will be minus 3 e minus 3x. Y second will be 9 e minus 3x. You know what? Let me do it this way. Maybe better. I will show you a method where you can check easily. Y1 prime will be minus 3. Y2 prime will be 9. Y third. This is the one, huh? That will be minus 27. E is minus 3x. Okay. I need to multiply this by 1. This is by 3. This one by 4. And this one by 12. It's when you put it this way, it will make it easy to check. So I have the third plus 3y double prime plus 4y prime plus 12. This by 1 minus 27, e minus 3x. 3 times 9 is 27, e is minus 3x. Minus 12, e is minus 3x. Plus 12, e is minus 3x. Very clear, this is cancelled, 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 cancelled. It's equal to 0, which is the right-hand side. So this is the left-hand side, and this is the right-hand side. So for sure, y1 e is minus 3x is a solution. Okay. I'll do the same for the next one. y2 is cosine to x. y2 prime only minus 2 sine to x. y2 double prime, it will be, this is 2x, minus 4 cosine to x. y2 triple prime, that will be what? 8 sine to x. I'll do the same. Multiply this by 1. This is by 3. This is by 4. This is by 12. And see what will happen. So now for y2, yeah, we need to check left-hand side, which is y2 triple prime plus 3 y2 double prime plus 4 y2 prime plus 12 y2. That should be equal to what? Plug the numbers. 8 sine to x. 3 times this minus 12 cosine to x minus 8 sine to x plus 12 cosine to x. Cancelled, 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 cancelled. That will be 0, which is the right-hand side. So y2 is a solution. Let me check the third one, y3. y3 of x. Now we'll start with sine. y3 prime. It's y2 cosine to x. y3 double prime. It will be minus 4 sine to x. y3 triple. That's equal what? Minus 8 cosine to x. So multiply this by 1. This is by 3. This is by 4. This is by 12. I'll check. Left-hand side is equal to what? y3 triple prime plus 3 y3 double prime plus 4 y3 prime plus 12 y3. And that equal to what? Just substitute. y3 double prime, multiply this by 1, minus 8 cosine to x. 3 times this minus 12 sine to x plus 8 cosine to x plus 12 sine to x. Clear, this cancelled, this one cancelled, so I'm getting 0 right-hand side. So y3 is also a solution. So that means any linear combination of those ones is also a solution. Now in the exam, how things like that will come. For sure, he will not ask you for a phi. What he will do, maybe he'll make it as a linear combination, or you put a constant somewhere. You put a value, and he make it cosine ax, for example, or e to the power alpha x. Find alpha. We'll make a constant somewhere, and then he asks you for that constant. We'll see it when we talk about the whole exams. Given that this, our solution, show that without substituting that this is a solution. Yeah, why is that? Because what the superposition is talking about. If you have solutions, any linear combinations is also a solution. So for sure, I have y equals c1 sine x plus c2 cosine x is a solution. This is superposition theorem. Now the other solution, this is for any C1, for any C1, C2. That means what? Now I can take C1 to be 2 and C3 to be 3. That means y equal 2 sine x plus 3 cosine x is a solution. So I prove that without substituting. Because you said, given that these are solutions of the differential equation. Okay, just this is to make sure we understand the superposition principle, and also how to verify a function is a solution of the differential equation. Okay, this is what we did up to now. Now let me go more. Existence and uniqueness of for a solution. If you have linear differential equation, if you have this linear differential equation, when we say this differential equation has a solution, yeah, has a unique solution, has a unique solution, one and only one solution. Note I make it in this form, in the standard form, where the coefficient of the derivative is 1. What I need those functions, these functions, and also f, to be continuous. To be continuous. Interval I containing the point A. And A also is very important for me. Okay. Yeah. That, by the way, this theorem can show, can give us, if we have this n derivative, this is nth order differential equation, and they have these conditions, then y of x as a zero function is the only solution. Given that, these b's are continuous. Because if these p's are continuous, then it means if there is a solution, then it has a unique solution. And for sure, y equals 0 is a solution. Why? Because if y equals 0, any derivative will be 0. So substitute left-hand side equal right-hand side. Very clear. So it's a solution and also satisfying the initial condition. So it's the only solution if all of these speeds are continuous. Okay. So that means this is the only solution for such problem, provided all the initial conditions are 0. Now we have to use existence and uniqueness theorem to find the largest interval so that the given initial value problem has a unique solution. So what's my A? A is 0. This is important. And also I need to rewrite this equation in a way to be in this form. In this form. Okay. So it means the n derivative will be the coefficient of the derivative should be 1. So I will divide by x minus 2. So I have y double prime plus ln x plus 2 over x minus 2y equal x over x minus 2. So I need to, how to say that there exists a unique solution? Has a unique solution. As in this theorem, they are when they have unique solutions, if P1, P2, Pn, and F are all continuous. And they want A to be in that interval. Okay. So I have P2 is 1, which is continuous everywhere. So this is minus infinity to infinity. Nothing to worry about. P1. The coefficient of y prime is 0. I don't have y prime. Okay. So it's like this is y double prime plus 0, y prime plus this. You can think of it this way. So coefficient of y prime is 0, so this is also continuous on minus infinity to infinity. Now it comes P0 of x is what? Is ln x plus 2 over x minus 2. And I know when how to check when it's continuous. I need two things. I need x plus 2 to be positive, and I need x not equal to 2. So let me do I need 2 to be out, and this is minus 2 greater than. So for sure the interval is what? Minus 2 to 2, union 2 to infinity. That's when this function is continuous. The last one, f of x over x minus 2, which means x not equal to 2, which is okay in this one, x not equal to 2. Now, is that means this is the interval where I have a unique solution for this problem? No. I need the condition, y at 0. He said it should be to be continuous in the open interval I containing the point A. So I need an open interval containing the point A, which is 0. So I need open interval containing A, which is 0. Now A is here. This is A. What will be the interval? Or the largest interval? Yeah, because any interval, it will be okay. Any interval containing 0 is okay. It means it has a unique solution. But he wants the largest interval. The largest interval will be it will be this interval. It contains A, and the function is continuous. So we can find also differentiable, so we can find the derivative. The largest interval should be minus 2 to 2. It's not 2 to infinity. Why? Because 0 is not there. This is not. And the other the function is not continuous in the other part of in other portions of this real line. Okay. So I think that will explain the existence and uniqueness. It's a good example. By the way, it's not in the book. Verify the functions and then find the solution satisfying the initial condition. Is the solution unique? Okay. Now, how to verify a function? The functions are continuous or solutions. First, I need to check if there are solutions. Like what we did before. I say y1. I need what? The second derivative, e to the power x, y1 prime. By the way, later in this when I combine the 3 sections, we'll talk about how to solve the differential equation. But until now, we did not talk about that. That will be e to the power x, y1 double prime will be the same, e to the power x. I need to multiply this by 1, and this is by minus 2, and this is by 1. So left-hand side, give me 1. Double prime, minus 2, y1 prime plus y1. That give me what? E to the power x minus 2 e to the power x plus e to the power x, which is very clear is equal to 0, which is the right-hand side. So that means y1 is a solution. Now let me go to the next one, y2, which is x e to the power x. We'll do the same. Now the calculation is a little bit complicated. Not that complicated, but it needs more work. Derivative product of two functions. I have e to the power x plus x e to the power x. That will be 1 plus x e to the power x. y2 double prime. It will be what? 1 plus x e to the power x plus e to the power x, which is 2 plus x e to the power x. And then I this by 1, and this is by 2, minus 2, the minus 2, yeah. And this is by 1. Okay, so left-hand side, y2 double prime minus 2 y2 prime plus y2. That will be equal to what? 2 plus x e to the power x, and then multiply by minus 2. Minus 2 times 1 plus x, and plus x e to the power x. So I have what? 2 e to the power x plus x e to the power x minus 2. Don't forget to have e to the power x here. Okay. Minus 2 e to the power x minus 2x e to the power x plus x e to the power x. These cancelled, and this with this cancel this one. So I have 0, which is the right-hand side. So y2 is the solution. y2 is the solution. Okay. Then, and I need to find the general solution for that. This is what we'll do later, but the general solution, if these are linear independent, we'll talk about it later, but this is what we will do. The general solution y equals c1 e to the power x plus c2x e to the power x. Now, to find the solution, satisfying the initial condition, it means they need to find the c's, those c's. How to find those c's? I will apply just the condition. I have y at 0 equals 3, and y prime at 0 equals to 1. So I need y prime. What will be y prime? It will be c1 ax plus c2. Yeah. Let me do y prime here. Put the conditions here, huh? Y at 0 to save space. So y prime is what? c1 e to the power x plus c2 ax plus c2 x ax. Okay. Now y at 0 equals 3. That implies what? E to the power 0 is 1. So I have c1. 0 times e to the power 0, that will be 0. c1 equals 3. And have y double prime, y prime at 0 equals what? Equals 1. That implies I have c1 to the power e to the power 0, that will be c1 plus c2. That will be equal to 1. From here, c1 equals 3. So I have c2 is 1 minus c2, which is minus 2. Minus c1, sorry. 1 minus c1. Since c1 is 3, 1 minus 3 is minus 2. So my solution, it will be 3 e to the power x, where c1 is x. I just substitute c1. C1 is 3, and c2 is minus 2. Minus 2x e to the power. So this is my solution. Is it a unique solution? Yes, it's a unique solution. Why? Because the coefficient of y double prime, this is 1. This is minus 2. This is 1. So I have, this is just to show it is continuous. P1 of x will be minus 2, continuous everywhere. P0 of x is 1, which is continuous. And f is 0, which is continuous. So for sure, yeah, any a will be satisfied. A equals 0, since it's continuous everywhere. So a equals 0 and a equals 0. So that means this is a unique solution. That's the only solution. Okay. Consider this initial value problem. Verify that y1 equal x squared, y2 x cubed are two different solutions. Yeah, and they are different. So y1 will be what? X squared. Yeah. By the way, there are, why not here? Here is if this, if we take each solution alone, they will not satisfy the initial condition. Now notice y1 at 0 is 1, not 3. And y2 at 0 is 0. So that will not satisfy the initial condition. these two equations, if we dealt with them separately. However, when I combine them with this general solution, this we call the general solution. Later we'll do this. Then I can find the C satisfying the initial conditions. In this case, it's a little bit different. Y1 of x equal x squared. It will satisfy the equation and satisfy the initial condition. Let us check it. I will check both. So they are different. They are two different solutions of the initial value problem. Because when we talk about uniqueness, we're talking about uniqueness for the initial value problem with this initial condition. As you may know, usually the solution of the differential equation alone, usually there are infinitely many solutions. They're not only one solution. And for example, in this case, e to the power x is solution, and any linear combination is also a solution. Remember when we did the superposition principle. But when you talk about initial value problem, that will make it a little bit different. I wish it's very clear. Okay, so now this one, y1 of x equal x squared, where I need to show that this satisfies both the initial value problem. So satisfy, I need to prove this, satisfy the differential equation and the condition. Okay, let us show that. I have y1 prime is 2x, y1 double prime will be 2. So for the equation, y1 multiplied by what? By x squared. This is my minus 4x, and this one by 6. So I have left-hand side, y1, not y1, x squared y1 double prime, minus 4x y1 prime, plus 6 y1. That give me what? 2x squared minus 8x squared plus 6x squared, which is very clear 0, which is the right-hand side. Also, y at 0 will be 0 squared, which is 0. And y prime at 0 will be 2 times 0, which is 0. So this one satisfies both the equations, satisfy the initial value problem. This is, they call it initial value problem. Okay, now let me go to the next one. Okay, for y2 of x cubed. Okay, I need to satisfy both the initial value problem, satisfy the initial value problem. No need to write it again. Okay, y2 prime will be 3x squared, y2 double prime, it will be 6x. I need to multiply this by x squared, and this one by minus 4x, and this one by 6. Okay, so check the equation, the differential equation. I have left-hand side, x squared y2 double prime minus 4x y2 prime plus 6 y2. That will be what? 6x cubed minus 12x cubed plus 6x cubed, which is 0, which is right-hand side. So it's a solution. And also y2 at 0, this is y1. y2 at 0 will be 0 cubed, which is 0. Okay. y2 prime at 0, it will be 3 times 0 squared, which is 0. So both satisfy the differential equation. From here, I'm getting in y1 and y2 are solutions of the initial value problem. Okay, but that will give us, that will make a problem for us. Why? Because we said if I have initial value problem, then the solution should be unique but you have now two different solutions. So why that does not imply the theorem? Because you need to be careful. I need the functions, these functions, to be continuous. So if you go back to the equation, to this equation, note I need the coefficient of y double prime to be 1. So I need to divide by this, 4 over x y prime plus 6 over x squared equals 0. I notice p1 of x and also p0 of x. They are not continuous, or they are continuous where? From minus infinity to 0, union 0 to infinity. But a is 0, so there is no way I can have an open interval containing 0 where the function is continuous. So the conditions of the theorem does not meet. Or we can say the differential equation or the initial value problem does not satisfy the conditions of the theorem. Yeah, maybe this way is better. Of the theorem. Yeah. Because like no way that I have an open interval containing the 0, because the function is not continuous at 0. So we cannot apply the theorem. Because with that we get two different solutions. So we cannot say that we have a unique solution for this. So this initial value problem, or we cannot conclude, we cannot say no, if they are not satisfying the condition, it does not have a unique solution, no. But we say no, that explains why this initial value problem does not have a unique solution. Okay, so what we did up to now, just to be sure, we define what's the meaning of linear, homogeneous, non-homogeneous, associated homogeneous. Sometimes to deal with the non-homogeneous, and this is deal with associated homogeneous. Then we have the superposition. If you have solutions, then any linear combination is also a solution. That means we have a solution space. How to revise the solution? We just substitute left-hand side equal right-hand side. And also they have initial condition. If you have any, or before that, existence and uniqueness. When I am sure that this differential equation has a unique solution, if we have all the coefficients of this, after I make the coefficient of the n derivative 1, I need to check these functions to be continuous. And I think we did some examples. And as I said before, we're talking about the initial value problem. I will talk about this. Now, how to check the initial conditions? You need to find the constant, the C's, and I think it's easy things. And this example where it's clear that this, because the conditions of the theorem does not meet, so we cannot apply the theorem. And just one thing I want to be sure about. So when we talk about, let me talk about, yeah, this one, for example. I have y double prime minus 2y prime plus y equals 0. When I talk about y1, which is e to the power x, this is the solution. And also any linear, combination, any scalar multiplication And also, let me say y equal CE to the power x is also a solution. So we don't have a unique solution for the equation. On the equation, we don't have a unique solution. Actually, when we solve it, we dealt with, we can prove this, just substitute into the equation, you will get it. Actually, when we solve it, we dealt with this solution, C1ax plus C2x e to the power x. This is for sure not unique. It's a solution. It's a solution of the differential equation, but not unique. Because if I have C11, C23, I have a solution. If I have C110, C2 minus 3, anything like that, it will have, we'll have different solutions. However, when we talk about uniqueness or unique solution, we talk about what? We talk about the initial value problem. This initial value problem, which is, what was the initial value problem? Y at 0 equal 3. Y prime at 0 equal 1. This initial value problem has a unique solution. So the differential equation itself, we cannot talk about unique solution for the differential equation because usually we have infinitely many solutions. But when we combine it with initial conditions, then there is a possibility to have a unique solution, a solution if satisfy the conditions, which is what was the unique solution? 3e to the power x minus 2x e to the power x when I combine them. I wish it's clear. Now we'll talk about linear dependence and independence, like what we did in with the vectors. This is the general way to define dependence and independence, where, yeah, I think we'll spend a long time doing this. Yeah, let me go and do it. If I have n functions, we say they are linearly dependent. They are linearly dependent. If I can combine them, I make a linear combination of them where I can find these C's, not all zeros. There exists constants, not all zeros. To show, this is to show they are linear dependent, just I will find C's so that I can have a linear combination of them, not all zeros. To show they are linearly independent, I'm saying what? I'm saying, you know, I tried all the C's and for sure, none of them, yeah, I'm trying all the C's and none of them will make it equal to 0, which is impossible to do that. So there is another way to do it, where we need to introduce what's called the Wronskian. What is the Wronskian? Wronskian easily, it's just you list the functions. Assume you have n functions, and then you list, this is as a row, but as a column, you list their derivatives. So you have f1 prime, f1 double prime, until you have, since you start with 0, you have until n minus the derivative, the n minus 1 derivative for f1. And do the same for f2, for fn. I want this determinant not equal to 0, provided that these functions are, this is the definition of the Wronskian. This is the definition of the Wronskian. This is the Wronskian for any function. This is the way to do the Wronskian, and they wrote it this way: W f1 f2 up to fn. However, I need this theorem. If I have solutions, if they are in solutions, y1 up to yn are in solutions for this nth order differential equation, homogeneous, then the Wronskian either is equal to 0, identically 0, or never 0. And if it is identically 0, we say these functions are linearly dependent. If it is never 0, we say these functions are linearly independent. But this is, don't forget the Wronskian. It's not like the vectors where I list the vector. No, This one I have only the functions, so I need their derivatives. First, second, and so on. We'll do examples to explain it. That's the meaning of dependence or independence. So to prove it they are dependent, just you need to find the C's. You need to find this linear combination. I cannot prove linear independent by finding linear combination because it means I tried all the C's, which is impossible to do. But I can do it through the Wronskian, provided they are solutions. Okay, given that these functions, he said these are already solutions. These are already solutions. And we already did that before. We checked that before. Show that they are linearly independent. Since they are solutions, I will do the Wronskian of y1, y2. What is that? y1, y2, let's write the formula. That will be y1 prime. I have only two functions. So we'll do this. y1 is e to the power x. This is x, e to the power x. What's the derivative? E to the power x. What's the derivative here? E to the power x plus x, e to the power x. Find the determinant. That will be what? E to the power 2x plus x, e to the power 2x minus x, e to the power 2x. And the answer is e to the power x, which is impossible to be 0. So for sure, y1 and y2 are linearly independent. Determine whether the functions are linearly independent or linearly dependent. Yeah. Okay. If you look at these functions, they are linearly dependent. Why? Because if you look at these two functions, this is what? 2 sine, cosine. Yes, this one has no relation to them, but these two, they are linearly dependent. They depend on each other. This very clear, f3, 2 times f3 give me f2. So it means what? Can I find C's where I can list these functions? Make it equal to 0. Yeah, let me check. C1, then x squared plus 1 plus C2 sine 2x, which is 2 sine x cosine x. And C3 sine x cosine x equals 0. I notice maybe some people they say this has no relation to that. Yes, but the idea, I need to find C's, not all zeros, satisfying this. The linear combination of these functions make it is equal to 0. So for sure, since this is 2 sine cosine, if I choose this to be 1 and I choose this to be minus 2, this will be 0. But that will make a problem? No. Make C1 0. So I satisfy the condition. Find C's, not all zeros. So it means F1, F2, and F3 are linearly dependent. Because I can't find C satisfying this initial, this linear combination. Yeah. If you have two functions, it will be very easy. Since if they are, if there is one of them is a constant multiple of the other or not, or what I will do, I just divide them. If I get a constant, that's it. If I get a function, no, there is a problem. And for example, this one, very clear, sine and cosine, they are linearly independent. Or should they are independent? Because if I divide them, I find this, I get what? Sine over cosine. I'm not getting a constant. I'm getting tan, not a constant function. So they are linearly independent. If they are two functions, 3 functions, for sure I need the Wronskian provide they are solution. And if you go back to this one, these two very clear they are linearly independent. If I take them just only these two, because if you take h of x f2 over f3. That will be 2 sine x cosine x over sine x cosine x. That give me 2, which is constant. So they are linearly independent, and that's what will make, if you combine it with other functions, for sure they are still linearly independent. Yeah, because they take these c's to be 0. Those ones, they'll make it linearly independent. Okay. X an absolute value of x. It's linearly independent with this interval because absolute value of x is what? Is x. If x is positive, minus x if x is negative. So if you have x over absolute value of x, that will be what? 1 if x is positive, minus 1 if x is negative. So that means what? This is not a constant. Not constant. So x, an absolute value of x, or let me say, yeah, f of x equal x, and g of x, absolute value of x, are linearly independent on this interval. However, if I take this interval, x to 0, if x greater than 0, what will happen? I have f of x equal x, and g of x equal x, absolute value of x, which is x. So they are, for sure, they are linearly dependent because they divide them, I get 1 in this interval. But in the general interval, minus infinity to infinity, they are linearly independent. Sine square, cosine square, and another function 7. Can I prove that they are linearly independent? Linearly independent, yes. I have C1 f of x plus C2 f2 of x. This is f1. Let me say f. I said f with g or h. G plus C3 h of x equals 0. I have C1 sine square. Can I find C's? Plus C3 times 7 equals 0. Yeah. I know that in the sine square plus cosine square is equal to 1. So what I will do, I will make this minus 7 and this minus 7. So these things will be minus 7. And this is, I'll make it 1. So minus 7 plus 7 equals 0. It means they are linearly independent. I can use the same trick here. I have a fourth function which is not related, but still I can do the same trick. I have C1 F1 plus C2 F2 plus C3 F3 plus C4 F4 equals 0. That means C1 sine square plus C2 5 plus C3 cosine square plus C4 EX equals 0. So what I will do, I will take this minus 5, and this is 1, and this is minus 5. So I know these two will give me minus 5 plus 5, that is 0, and this will make it 0. So for sure they are linearly dependent. Okay. As I said before, if you have two functions, so you check if they are, when they are linearly independent, if when you divide them, you get a constant function for all x belongs to the I. When I say they are linearly independent, if I'm getting not a constant function. Sine, cosine, I think we did. Very clear. This one, if we divide AX, or let me say F2, the same, F2 over F1, I'm getting what? X squared e to the power x over x squared, which is x over e to the power x. I'm getting x squared, which is not a constant function, so they are linearly independent. Also, these ones we did before, they are linearly independent. Yeah. X and absolute value of x we did before. 0 to x plus 1. Yeah. If I have 0, then for sure, if you have a function 0 with any functions, any selection of functions, for sure it will be linearly dependent. Because why? I can do it two ways. C1 F1 plus C2 F2 equals 0. So I have C1 times 0 plus C2 times 2x plus 1 equals 0. I take C1, what I will do, I'm doing the different colors. C1, I take it any value, 1. C2, take it 0. So for sure, this is the combination where not all t is 0. So they are linearly dependent. Also, if I divide 0 by this, I'm getting 0. Yeah. Let me go back to this 0. Let me do another example. Assume I have this. F1 equals 0. F2 equal x. F3 equal e to the power x. F4, make another combination, cosine x. Well, I'm sure these functions are totally different. They are not, but since I have the 0, one of the functions, I can write a linear combination, C1 F1 plus C2 F2 plus C3 F3 plus C4 F4. I'll make it equal 0. Because what I will do, I will take all the C's to be zeros, this 0, this 0, this 0. But this one, I take it a value, because 1 times 0 is 0. Or take it 3, take it 10, who cares? So for sure, I can have a linear combination where not all C's are zeros, and let's make it equal to 0. So because of that, they are linearly dependent. So if we have one of the functions is a 0 function, for sure, this collection of functions will be linearly dependent. Now I have sine square and 1 minus cosine 2x. You need to be careful. This one, cosine to x, I need to relate it to sine square. I know the cosine to x is what? Is 1 minus 2 sine square x. So 1 minus cosine to x is what? 1 minus 2, that will be 2 sine square x. So that actually is 2 sine square x. So if I divide them, I'm getting a constant. Or if I do that C1, C2, I have C1 F1 of x plus C2 F2 of x equals 0. Yes, I can do this. How? By selecting this C2 to be 1 and this C1 to be minus 2. So I have minus 2 sine squared plus 2 sine squared. That will be 0. It means they are linearly dependent. This one, C1 times x squared plus C2 sine 2x, which is, don't forget, sine x cosine x. That of sine 2x plus C3 times 4 sine x cosine x equals 0. Can I find C's? Yes. How I do that? I make this 0. This one is 2, so I multiply by 2, and this multiply by minus 1. So I have 4 sine x cosine x minus 4 sine x cosine x plus 0. That will be 0. So they are linearly. Last one. I have C1 e to the power x plus C2 cosine hyperbolic x plus C3 sine hyperbolic x equals 0. Don't forget, cosine hyperbolic x plus sine hyperbolic x is equal e to the power x. You know this formula from Math 101. Yeah, since this is e to the power, easy to prove. Over 2. And this is e to the power x minus minus x over 2. So that it will be e to the power x. Very easy to prove. So what I will do, I will take, this is to be 1, this is to be 1. So I have cosine hyperbolic plus sine hyperbolic equals e to the power x, and take this minus 1. So for sure, they are linearly dependent. Now we'll have this theorem where I will stop. The general solutions, homogeneous equations. How to find the general solutions? I need solutions. These solutions, not only solutions, they are linearly independent, and they are, I have int order, and they are n. So you have n linear independent and solutions. Then, if that is the case, then we say we have the general solution. Then we have the general. That will be the general solution, which is just a linear combination of that. I'll talk about that, inshallah, in the next video. I'll stop here. I think I have enough good number of examples. Let me stop the recording. Thank you.